In this video, we'll talk about optimization problems. Optimization is the process of finding absolute extrema, or optimal values, for a function on some domain, possibly an infinite one. Let's look at the steps involved in solving optimization problems. The first step is to read the problem and identify the unknown quantities. What quantity is supposed to be optimized? Step 2. Draw a diagram or picture to help organize the information, if appropriate. Step 3. Introduce notation, labels, variables, etc. You might use the first letter of the name of a quantity as a label for it. L could be length, W width, H height, A area, V volume, and so on. Or you might just use X and Y. Step 4. Find a formula for the quantity to be optimized in terms of the other variables. This quantity is called the objective because it's the thing that you're trying to optimize. Area equals length times width, or volume equals length times width times height. Most problems will have some sort of restriction on the variables. Express this restriction as an equation in terms of the variables you have introduced. This is known as the constraint equation, and it provides the constraint. It also gives you a way to rewrite the objective function as a function of one variable, and that's what you do in step 6. This is called the objective function because it achieves the objective as a function of one variable, which you can then optimize using the standard techniques. And that's what we do in step 7. We identify the domain of the objective function and find the extreme values over this domain. If the function is continuous on a closed interval, then you know that it has optimal values by the extreme value theorem. But it's very possible that you'll have an unbounded interval, an infinitely wide interval, or you might have an open interval. In these cases, you still need to do it in pretty much the same way. You find all of the critical points, you determine what the value of the function is at the critical points, but instead of evaluating at the endpoints, if you have an open interval or something which is infinitely long, then what you do is you look at the limiting behavior. Look at the function as it approaches the endpoints. See what happens. Maybe it doesn't have a minimum. Maybe it doesn't have a maximum. That's really what you want to determine. Let's start with an example. Find the smallest possible product of two numbers if their difference is 10. Okay, well, in this example, there are no pictures to draw, and there are no specific labels that we need to use. We can just let x and y be the numbers. Let x, y be the numbers. What do we know? We want to find the smallest possible product. So that means that our objective is to determine the product, which I'll call P, and that's just x times y. We can also determine our constraint. We know that their difference is 10. So one of these two numbers must be bigger than the other. So we might as well just assume that x is bigger. So assume x is bigger than y, and then our constraint is that x minus y is equal to 10. So that's our constraint. In particular, it tells us what one variable is in terms of the other. So we can just write, for example, x equals 10 plus y. X is 10 more than y. Now we can take this value right here and we can plug that into our product right here for x. And so that will give us our objective function. So our objective as a function, the objective function, is going to be some p, but it's going to be evaluated at one variable, in this case y, because we're going to write x as 10 plus y times y. So this is our objective function, which we can expand. So this will be 10 times y plus y squared. And That's our objective function in terms of the one variable y. Okay, well what we want to do is we want to optimize this. Over what is the question? What is our domain? Well, in this case, our domain is the set of all real numbers. Because it just says find the smallest product of two numbers. There's no other restriction on these. There's no restriction on our domain. So the domain is the set of all real numbers. Okay, so that means we don't necessarily have what we want thanks to the extreme value theorem, because that's only valid on closed bounded intervals, and we don't have that here. But we still proceed in pretty much the same way. We find the critical numbers, and then we check asymptotic behavior. It'll become more apparent when we start working on this. So let's optimize. We start by computing the derivative. So p prime at y is equal to 10 plus 2y. We set this equal to 0 and solve for y. We get that y is equal to -5. Okay, and that's our critical number. The corresponding x is going to be what? Well, x is equal to 10 plus y, so that's 10 plus a -5, which is 5. So that tells us our one critical point is the one where x is equal to 5. So let's just write it as a point, 5 comma -5. So x is equal to 5, y is equal to -5. And this is actually just what we're looking for. So if we go back to the question, find the smallest product of two numbers, well, we found the two numbers, or have we? Let's figure out what the product is here. So p at -5, well, really that's just x times y, right? So that's just going to be 5 times a -5, which is a -25. So the claim is that this is the smallest product. Now, if this were a closed bounded interval, we could just check the endpoints and see if they were bigger. Now, in this case, we can't do that, but there are a couple of different ways that we can proceed. We could, for example, just look at the limiting behavior. If we look at p at y, this is equal to 10y plus y squared. Now you can look at that asymptotic behavior as y goes to infinity or minus infinity, and because of this y squared term, this is going to become infinitely large. So as you move further to the right and further to the left, you're going to get something larger than -25. Another way you could proceed is, since this is a parabola, you could just find the vertex of the parabola. This is a parabola opening upwards, so if you complete the square, it's easy enough to find the vertex, and that will definitely be a minimum. Now, another thing you could do is just look at the derivative. We know what the derivative is. It's p prime of y equals 10 plus 2y. Well, check out the second derivative in that case. So if p prime of y, let's just rewrite this, is 10 plus 2y, then the second derivative is just 2. And notice that's always positive. So this is concave up. So what does that tell you? If you have a critical point and the function is concave up there, then that tells you that you must have a local minimum. So by the second derivative test, there is a local minimum at y equals -5. So -25 is a local minimum value. But here's the thing, if you have just one critical point and it's a local minimum, it must be the absolute minimum. Because if there was a lower value, a smaller value anywhere, then there would need to be another critical point. Well, what do I mean? If you just take a look at the graph of a local minimum, it's going to have some kind of shape like that, right? So we can imagine that we're here. This is a local minimum. Now, if it wasn't the absolute minimum, that would mean that at some place the function, the graph must get lower. So the only way that it can get lower is if somewhere it turns around like that. But if it does that, then notice what you get. You get a local maximum. So if you have a continuous function and you have one local minimum and no local maximums, then that local minimum must be an absolute minimum. So this is sort of a general rule or a general principle. Let's just call it general rule here. And that's if f is continuous, and has only one local extreme value. Well, actually what I want to say is it has only one critical point. Then if it is a local min, it must be an absolute min, if you'll excuse my abbreviating here. And if it is a local max, it must be an absolute max. So let's number these in no particular order. So the basic idea here is that if f is continuous and has only one critical point, then if it's a local minimum, it must be an absolute minimum. If it's a local maximum, it must be an absolute maximum. And the basic idea comes from this drawing. So if you have one local minimum, then the only way you can have another value of the function which is lower is if somewhere there's a local maximum, because it has to turn around somewhere. So if you only have one local value and it's a minimum, it must be the absolute minimum. Similarly, if you have one local maximum, the only way you can possibly get any values that are larger is if somewhere along the way the curve turns around and you get a local minimum. So that's one way to solve these optimization problems. Okay, so if we go back, we'll notice that we actually solved this problem a while ago. The absolute minimum for this problem is negative 25. So negative 25 is the smallest product that you can achieve with two numbers where their difference is 10. And you even found the two numbers, 5 and negative 5. Let's do another example. If two positive numbers sum to 16, what is the smallest possible value of the sum of their squares? Okay, so here we're just looking at two numbers again, but now instead of looking at their product, we're looking at the sum of their squares. So once again, let's just let x and y be the two numbers. Now we know that they're two positive numbers, so that means that x is greater than 0 and y is greater than 0. What else do we know? We know that their sum is 16, so we have that x plus y is equal to 16. Well, this is actually the constraint. What is it that we're trying to determine? We want to find the smallest possible value of the sum of their squares. So x squared plus y squared. This is the objective quantity. Now we want to write this as some sort of function, so let's call it s for sum of squares. This is x squared plus y squared. But it's a function of two variables. So we're going to take this constraint and we're going to solve for one of the variables. Let's say x is equal to 16 minus y, like that. Okay, so now we can just take this value for x and plug it in here. So s as a function of y will be 16 minus y, quantity squared, plus y squared. Okay. So now we have a function of one variable, and this is the objective function. So what are we going to do with it? We're going to optimize it. What is our domain? Well, our domain here is the set of all y values greater than 0. So y is a number greater than 0, so our domain is the set from 0 to infinity. So again, this is not a closed bounded interval, but that's okay. We're going to proceed in pretty much the same way that we did last time. So we start by looking at the critical values. S prime of y is, and we could multiply all that out, or we can just use the chain rule. So this is 2 times 16 minus y times the derivative of what's inside, which is minus 1. Don't forget the minus sign there, plus 2y. So the derivative of y squared is 2y. And we have 16 minus y quantity squared. So if we differentiate that, then we have something raised to the 2 power. So that's going to be 2 times that thing, and then it's going to be times the derivative of that thing. So this is the derivative with respect to y of whatever's inside, 16 minus y. And that's just going to be minus 1. So it's easy to lose that minus sign, so be careful about that. So this is going to be equal to, if we multiply all this out, we're going to have 2 times 16 times the negative 1 is a minus 32. 2 times negative y times the negative 1 is plus 2y, which is negative 32 plus 4y. So that gives us our derivative. S prime of y is equal to negative 32 plus 4y. We want to find the critical points, so you set that equal to 0, and then just solve for y. So 4y is equal to 32, and y is therefore equal to 8. Okay, so this is actually going to give us the value that we need, because what do we know? We know that x is equal to 16 minus y, so we're going to have that x is 16 minus 8 is 8. So x is equal to 8, y is also equal to 8. Okay, well, we should probably figure out if this is actually our absolute extreme value. Now let's just go back to the question here, and we want the smallest possible value of the sum of their squares. So we want to make sure that this gives us an absolute minimum. And how are we going to check that? Well, we can do exactly what we did before. We can look at the second derivative. S prime prime of y is equal to 0 plus 4. So it's 4, which is greater than 0. So what does that tell us? That tells us that it's concave up everywhere. For all values of y. So that tells us that we have one critical number. So we have one critical point, I'll just abbreviate it, at y equals 8. And we also have that it is a local minimum, again using the second derivative test, because we know what the concavity is. We know that it's concave up, so that means it's a local minimum. But if you have one critical point and it's a local minimum, then it must be the absolute minimum. Therefore, we have an absolute minimum value when y is equal to 8. And now it just remains to determine what that value is. Well, we know that s is equal to x squared plus y squared, and we know what x and y both are. So that's going to be 8 squared plus 8 squared, which is 64 plus 64, which is 128. So that's the smallest sum of the squares for two numbers who sum to 16. Okay. Example 3. A rectangular pen for sheep has one side against a barn, while the other three sides are made of a wire fence that costs $5 per foot in length. Find the minimum cost of such a pen that encloses 32 square feet. So Finally, we've got a problem where we can draw a picture. So what do we have? Well, we have a barn. So let's just draw the barn here. We'll label it so we know that it's a barn. And then we're going to have a fence. And we know that it's a rectangular pen, so it's going to look something like this, let's say. Okay, now that's supposed to be a rectangular pen, so let's just draw it like that. Okay. All right. So what we're interested in is finding the minimum cost of making this rectangular pen, given that it must enclose 32 square feet. So this must be area equals 32 square feet. And we're only worried about the sides of the pen that are made of the fence. The barn is already here, so that means we don't need to build that. The barn already exists, so that's already there. Okay, so how are we going to do this? Well, basically we're just going to start by assigning some labels. We know it's rectangular, so let's call one side X and the other side Y. You could also call them L and W if you wanted. Any letters that you want, so long as they aren't being used for something else already. Now, if you use it this way, then we know a formula for the area. And so that's x times y is 32. Now, this is the constraint. What is the objective? Well, the objective is the cost. So if we let c be equal to the cost, then it's going to be 2x plus y, that's the total length, times $5. Right? Because the total length is x feet plus x feet, which is 2x, plus y. So 2x plus y. This is the total number of feet. So this is the total fencing in feet. And it costs $5 per foot. So that just tells you that the cost will be $5 times the total number of feet. So in other words, C is equal to 10x plus 5y. And this is our objective quantity. What we want to do is optimize this in some way. We want to find the minimum cost. So we want to minimize this. Well, the first thing to do is turn it into a function of one variable, and that's where our constraint comes in. So we know that x times y is 32, so y is equal to 32 over x. We can just plug that into c, and we'll get a function of just x. So it's going to be 10x plus 5 times 32 over x. Now what's our domain here? Well, x is a length, so you could make x as long as you want, at least in theory, but as x gets longer, in order to make sure that the area is fixed at 32, then this y would have to get more and more narrow. So you could make this rectangular pen very long but very thin. Now if you did that, you would actually be making your pen cost a lot more because you're paying by the foot. So you wouldn't want x to be infinitely large, but at least in theory it could be. Now what is the domain? Well, x is a length, so x has to be bigger than 0. And, well, what about less than? Well, in theory, you can make it infinitely long. You wouldn't want to because the longer x is, the larger x is, the longer the fence is, and the more it would cost. And in fact, you can see from looking at the equation that the larger that x gets, the larger the cost will become, because this term will become larger and larger. So as x goes to infinity, this will become infinitely large. It will increase without bound. And actually, this term tells you that x can't go towards 0, because as x goes to 0, this term will become infinitely large, growing without bound. And that's simply because the smaller x is, the larger y has to be to compensate, because remember the area is fixed at 32. So just like when x became long, y had to become narrow, We also have that if x becomes narrow, then y has to become long to compensate for that. So you don't want x to be too close to 0 or too close to infinity. Well, it can't be close to infinity, but you don't want it to be too large. Okay, so how are we going to determine the optimal value? Well, we're just going to differentiate. Do what we did before. So c prime of x is going to be 10 plus 5 times, and what's the derivative of 32 times x? Well, this thing right here, this is 32x to the negative 1. So if you use the power rule, that's going to be minus 32x to the negative 2. So that's 10 plus 5 times a negative 32 over x squared. Now, you might be wondering why I haven't actually just multiplied 5 times 32. That's because I'm about to set this equal to 0. And once I do that, I'm going to now solve for x. And I'm just going to end up canceling out that 5 anyway. Okay, so let's just rewrite this here. We'll have 10 minus 5 times 32 over x squared equals 0. So we can just add that term to both sides, and we'll have 10 equals 5 times 32 over x squared. Now we divide by 5 times 32, so we'll have 10 divided by 5 times 32 is 1 over x squared. And so what does that give us? Well, 10 is 5 times 2, and then in the denominator we have 5 times 16 times 2 is 1 over x squared. So of course this 5 cancels with that 5, this 2 cancels with that 2, and we have 1 over 16 is 1 over x squared. So that tells us that x squared is equal to 16. So x is equal to 4, or x is equal to negative 4. Well, of course, x can't be equal to negative 4 because it's the length of fencing, so it's got to be 4. So we have one critical point, and that's where x is equal to 4. And furthermore, we can determine what kind of critical point that is by looking at the second derivative. So we know that c prime of x is equal to, let's just rewrite this, 10 minus 5 times 32x to the negative 2, and now we want to just differentiate that. Now we already know that this is going to be a minimum value because we already talked about the fact that as you go as x goes towards 0 or infinity, this becomes arbitrarily large. But we're just going to confirm that using the second derivative. So the derivative of 10 is 0, and then you're going to have minus 5 times 32, and then differentiate x to the negative 2. That's minus 2x to the negative 3. So what are we going to end up with? We're going to end up with, this is actually 320 over x cubed, because 5 times 2 is 10 times 32, 320. The minus signs cancel, and then x to the negative 3 puts the x cubed in the denominator. Now, what's important here is that on our domain, x is greater than 0. So that tells us that c prime prime of x, which is 320 over x cubed, is greater than 0. So that tells us we're concave up. So that tells us that our critical point, which is x equals 4, is a local minimum. But again, there's one critical point, it's a local minimum, so it must be an absolute minimum. X equals 4 gives an absolute minimum. X equals 4 isn't the minimum, it's the x value for the minimum. What is that minimum value? Well, remember what the cost function was. Cost of x. Well, if we go back, this is our formula right here. 10x plus 5 times 32 over x. And now we just take that x equals 4 and just plug it in there. And so our minimum cost will be c at 4 equals 10 times 4 plus 5 times 32 over x, but x is equal to 4. And of course that's 8. So we're going to have 10 times 4 is 40, plus 5 times 8 is also 40. So we're going to end up with 80. The minimum cost is $80. $80 with dimensions x equals 4 and y was equal to, and if we just remind ourselves what y was, if we go way back, y is equal to 32 over x, and 32 over 4 is this value right here, it's 8. So y is equal to 8. So these are the dimensions right here. So we want a 4 by 8 rectangular pen, and that will give us a minimum cost of $80. Now again, we didn't actually have to look at the derivative because we saw that the formula, so if we go back here, the formula for cost is 10x plus 5 times 32 over x. And as x goes to infinity, this becomes arbitrarily large. And as x goes to 0, this becomes arbitrarily large. So that tells us immediately that whatever critical value that we have, it's going to be the minimum value because there is no maximum value. Okay, let's do another example. Example 4. A box with square base and no top has volume 32 cubic centimeters. Find the dimensions of the box that minimize the amount of material used to make the box. That is, find such a box with minimum surface area. So what does the box look like? Well, it's a rectangular box, and it has square base, but it has no top. So if it has square base, then it's going to look something like this. If we try to make this look reasonably square-like, but it has no top, so you can see inside. There we go, something like that. Let's just get rid of that little bit there. Okay, so it looks something like this. We're assuming that it has a square base. So if we make this measurement x along the base, then it's a square, so it's x by x. The height, we can just call it some other letter. We could call it h, but since I used x, might as well use y here. Okay, so what do we know? We know that the volume, is x times x, which is x squared times y, is equal to 32. That's given to us. So this is our constraint. What is it that we're trying to optimize? We're trying to optimize the surface area. We want to find the minimum surface area because that will result in the least amount of material. So in other words, that will be the cheapest box because you need the least amount of material to make it. Okay, so we need a formula for the surface area. So the surface area is going to be equal to, well, let's just imagine drawing in the rest of this box here. So it's going to look something like that. That's not quite straight, but it's good enough. Okay, so if we want to compute the surface area, notice that we have at the bottom here, we have one surface which is x by x. So we're going to have an x squared plus, and we don't have a top. That's important. If we did have a top, we'd have another x squared, but we don't. So instead we have one face along the front here, and one face along the back, and along either side, but those are all x by y, and we have 4 of those. So let's just shade in one of them here. So this one, that's an x by y, but we actually have 4 of those, so it's 4 times x times y. So that's the surface area. Well, this is the objective. Now, in order to proceed, we need to take the constraint and solve for one variable in terms of the other, and then plug that into the surface area. So it looks a little bit like it will be easier to solve for y, so we write y equals 32 over x squared, and you just take this value and plug it right in there. So then you'll have the surface area is a function, let's just call it s, it's a function of x, and it will be equal to x squared plus 4 times x times y, which is now 32 over x squared. And so this will give us x squared plus 4 times 32 over x, which is equal to x squared plus 128 over x. Okay, we didn't actually need to multiply those two together because later on there's going to be some nice canceling that happens. But this is our objective function. This is the thing that we want to optimize. Well, in fact, we want to minimize. Okay, so how are we going to do it? The same way that we always do. We just compute the derivative. So s at x, let me just rewrite this as x squared plus 128 times x to the negative 1, because we're going to use the power rule. So we'll have 2x minus 128 times x to the negative 2. And now that we've done that, it's a little bit easier to write it as 128 over x squared. And, well, we need to ask where this will equal to 0. There's also a place where it doesn't exist, but that's when x is equal to 0. And again, we're looking at dimensions, so I probably should have written the domain here. So x is greater than 0 because it's a dimension. So that's really the only restriction, at least in theory, that we're going to make. So the domain will be the numbers from 0 to infinity. So x can't be 0. So instead we just set this equal to 0 and solve for x. Let's just start by rewriting this. 2x minus 128 over x squared equals 0. So we just add this term to both sides. We'll have 2x is equal to 128 over x squared. And that gives us, if we multiply by x squared on both sides, we'll have 2x cubed equals 128. Now what is 128? That's 2 times 64. So x cubed is equal to 64, which means that x is the cube root of 64, which is 4. Okay, so x is equal to 4. And now we can determine what y is if we just go back to our formula, which is right up here. Y is 32 over x squared. So y is 32 over x squared, 4 squared, which is 32 over 16, which is 2. Okay, so x is equal to 4 and y is equal to 2. So the dimensions are 4 by 4 by 2. Now we should probably just determine that this is in fact a minimum, but again it is because we can look at the second derivative. We have one critical point and we can show that it's a local minimum, therefore it will be an absolute minimum. So let's just rewrite our derivative here. So we're just going to check that x equals 4 is an absolute minimum. Just want to confirm that. So s prime of x is just 2x minus 128 over x squared, which is 2x, just to write it as something to a power, so it's 128x to the negative 2. And now we just compute the second derivative. So this is going to give us 2 minus 128 times negative 2x to the negative 3. And what's important here is you're going to end up with 2 plus 2 times 128, which is going to be what? 256 over x cubed. So in particular, this is positive since x is positive. So that tells us that we have, because this is using the second derivative test, because this tells us that we're concave up, we have a graph which is concave up. We have a local minimum at x equals 4, but this is the only critical point. So the function is continuous on its domain. We have one critical point, which is a local min. Therefore, the absolute minimum is when x is equal to 4, and of course y then is equal to 2. So the dimensions are 4 by 4 by 2. Okay. Let's do another example. Find the dimensions of the rectangle of largest area that has its base on the x-axis and its other two vertices above the x-axis and lying on the parabola y equals 8 minus x squared. Well, this is the kind where you really want to draw a picture. So the first thing we want to do is graph our parabola. So let's just draw some axes here. Actually, for this, let me just change my color. So we're going to draw an x-axis and a y-axis, and we're going to try and draw a parabola. It's a parabola opening downward, so it's going to look something like that. And this is y equals 8 minus x squared. Now, what we know is that our rectangle has base along the x-axis, and its upper vertices will intersect the parabola somewhere. So let's just draw in a rectangle like that. So we'll just draw in something. So this is our rectangle. And let's say that this point right here has coordinates x comma y. So in particular, that means that this y is equal to 8 minus x squared because it's on the parabola. But we now have a geometric interpretation of x and y. So x is the width of this, or at least half of this rectangle, and y is the height of the rectangle. So y is the height. Now what we're looking for is the dimensions of the rectangle of largest area. So the largest area will not be x times y because this width is also x over here. So the dimensions are going to be 2x by y. So we just need to figure out what x is and then multiply it by 2. 2x by y. So we're trying to find the largest area. Now the area, of course, is this area. We're trying to find the area of this rectangle. So what is that area going to be? The area is going to be 2x times y. And this is our objective. What is our constraint? Well, our constraint is actually this equation, because we know that there's a relationship between y and x. So our constraint is y equals 8 minus x squared. So we can take this constraint and plug it directly into our area and get our objective formula. So a, so the area, well, let's call it a, is a function of just x, and it's 2 times x times y, which is 8 minus x squared. Which we can write as 16x minus 2x cubed. So this is our objective function. So this is the objective function. And we want to optimize this. We want to find the largest area, so we want to find the maximum area. What is our domain here? Well, so our domain, these are the possible x values. Well, the smallest x could possibly be a 0, and we're not going to actually include 0 because that's, if x was equal to 0, then you'd have a straight line rather than a rectangle. And it would just be that straight line. So the area would be 0. So it's certainly not the maximum. And the largest that x can be is wherever it intersects the parabola. So we need to figure out what this intercept is right here. So what is this x value for that intercept. And we can figure that out. Let's just change the color here for a moment. Let's just change it to that color. So the x-intercept, that's when y is equal to 0. So this is going to be 0 equals 8 minus x squared. So x squared equals 8. So x equals plus or minus the square root of 8. So the coordinates of this point right here are square root of 8 comma 0. And this point over here, its coordinates are opposite of square 8. Opposite of square root of 8, 0. Okay, so that's the maximum possible x value you can achieve. So that's the maximum possible x value that you can plug in. So that's the limit. And again, we're not going to include that because if we did, we wouldn't have a rectangle anymore. We would just have a line. But that also tells us that we're not going to have a minimum because you can always get an area which is smaller. You can get an area which is arbitrarily close to 0 just by making this x either be closer to 0 or closer to square root of 8. So either way, you'll end up with something which is arbitrarily narrow. So the maximum area will be somewhere in the middle here, and we can figure out what it is using our usual techniques. Okay, so we want to optimize this area function. So that's 16x minus 2x cubed. We need to compute the derivative, so a prime of x, just using the power rule, so this is going to be 16 minus 2 times 3 is 6x squared. So we just set this equal to 0. And what are we going to have? We'll have 16 equals 6x squared, or x squared equals 16 over 6, and we can reduce that. That's 8 over 3. So that tells us that x is equal to the positive square root of 8 over 3, or x is equal to the opposite of the square root of 8 over 3. Well, x is positive because we're choosing x to be a point in the first quadrant there. Or rather, we're choosing x so that x comma y is a point in the first quadrant. So x is positive, so we know that x is positive. So we want x greater than 0, so we choose x is equal to the square root of 8 over 3. And now we can figure out what y is. So y, remember, is 8 minus x squared. That was our formula. Y is 8 minus x squared. So we know what x is now, so it's 8 minus the square root of 8 over 3, quantity squared. So that's 8 minus 8 thirds. So we have a whole 8 minus a third of an 8, so that's going to give us 2 thirds of an 8, which is 16 over 3. So that's our y value. So therefore, the dimensions are, well, remember they're not x by y, because if we go back up to our picture, it's 2x by y. So it's going to be, so it's 2x by y, if I can write it out like that. So that means the dimensions are 2 times the square root of 8 over 3 by y, which is 16 over 3. Those are our dimensions. Now we actually should probably double check to make sure that this is a maximum. We know that it is, because if we go back to our picture, we know that if we look at the extreme values, our area will be 0, or arbitrarily close to 0. So if you look at the endpoints, you'll find that the area gets smaller. So you can definitely conclude that these are the dimensions that maximize it, but you can also just look at the second derivative. We know that a prime of x, if we just go back up to where it was, a prime of x is 16 minus 6x squared. So 16 minus 6x squared. So a double prime a prime prime of x, the derivative of 16 is 0, so it's going to be 0 minus 12x, so that's just negative 12x. And we know that x is positive, so x is equal to the square root of 8 over 3. X equals the square root of 8 over 3, so in particular it's positive, so that means that a prime prime at this value of x, the square root of 8 over 3, is minus 12 times the square root of 8 over 3. But in particular that's negative. So what does that mean? That means you're concave down. And if you're concave down, that means we have a local maximum at x equals the square root of 8 over 3. But as before, you have a continuous function. It has one critical point, and that belongs to a local maximum, so we conclude that it's an absolute maximum. Is an absolute max at x equals the square root of 8 over 3. So the largest, or the maximum, area happens when the dimensions are 2 times the square root of 8 over 3 by whatever our y value was, and that was 16 over 3. 16 over 3. Okay, well let's just do one more example. What points on the curve y equals 1 over x are closest to the point 0, 0? All right, so let's just draw the graph. I'm just going to change the color a little bit. So we're going to have our axes here, and it's going to just look something like that and something like that, although that's not exact. Now what we're trying to do is we're trying to find the point on the curve which is closest to 0, 0. Well, there will actually be two, because whatever point over here you find, there will be a corresponding one over here. So basically what we're going to do is we're just going to pick a point here, and the point will have coordinates x, y, and we're just going to measure the distance from the origin, and we can just call that d for distance, I guess. And so d is equal to the square root of x squared plus y squared. And this is our objective. We want to minimize this. I want to minimize this quantity. Well, there is a constraint. It's this equation, because we know that this y is equal to 1 over x. So that tells us that the distance, well, let me just write it this way, distance is equal to the square root of x squared plus 1 over x squared. So that's the distance, and this is the quantity that we want to minimize. Now, actually what we're going to minimize is we're just going to minimize the thing inside. So we will minimize x squared plus 1 over x squared, because if that's as small as possible, then the square root of it will also be as small as possible. So let's just call this quantity something. We don't necessarily want to call it d, because we're already using d for something. So let's just call this f at x. Kind of want to avoid d anyway, because d usually means derivative. So let's just let f at x equals x squared plus 1 over x squared. And this is the thing that we're going to minimize. This is our objective function. Now, what is the domain of our function? Well, x could actually be anything as long as x was not 0. So our domain is negative infinity to 0, union 0, infinity. Now, if you wanted to, you could just restrict your attention to the right side, because whatever you find here, you'll find something corresponding to it over here. Now, one thing that you might notice is that as you approach 0, your quantity f will become arbitrarily large because of this. So let's just note that as we approach our endpoint, so the limit as x approaches 0 of f at x, you're going to get infinity, regardless of which direction you approach, because everything's positive here. It's x squared plus 1 over x squared. So as x gets close to 0, this quantity becomes infinitely large. And also, the limit as x goes to infinity, or minus infinity for that matter, of f at x is equal to infinity because of this x squared term. So as x goes to infinity or negative infinity, this thing will become arbitrarily large. So there is no point with maximum distance, but there will definitely be a point with minimum distance, and we can figure it out just by differentiating f. So f prime of x is going to be equal to, well, let's just rewrite f. So let's write it as x squared plus x to the negative 2. So the derivative, just using the power rule twice, is going to give us 2x minus 2x to the negative 3. So 2x minus 2 over x cubed. And we want to find out when that is equal to 0. So 2x is equal to 2 over x cubed. So you can cancel out those 2's, and you'll have x is equal to 1 over x cubed, multiply by x cubed, then you'll have x to the 4th equals 1. So what does that tell you? That tells you that x is equal to 1 or x is equal to minus 1. And both of these will work. When x is equal to 1, y is equal to 1 over 1, which is 1. And when x is equal to negative 1, you have that y is equal to 1 over negative 1, which is negative 1. So the 2 points are 1 comma 1 and minus 1 comma minus 1. So if we just go back to our picture, that's about right here. So this is x equals 1, 1 comma 1, and you have the same sort of thing right about here. So this length is 1, but that point is minus 1. So minus 1 comma minus 1. There we go. So these are the points of minimal distance. And you can just check that these are, in fact, minima. So all we have to do is just look at the second derivative again. So f prime, let me just rewrite this here. This is 2x minus 2x to the negative 3. So we differentiate that again, and we'll have f double prime of x is equal to 2. Then it's minus 2 times a negative 3 x to the negative 4, which is 2 plus 6 over x to the 4. And in particular, that's always positive. So what are we looking at? We're looking at local minima, because this thing tells us that we are concave up for all x. Now, we're not talking about the original graph y equals 1 over x. We're talking about this function right here. This function is always concave up. And because of that, we know that our local extreme values are both local minima. Now, keep in mind that there's a discontinuity between them because we're not allowing x equals 0. We're not allowing x equals 0. So we have a part over here where all of the x's are positive, and we have a part where all of the x's are negative. So basically, you just want to think about this as two separate problems. One where you're looking at the interval from 0 to infinity, where you have one local minima, and then you want to look at the part from negative infinity to 0, where x is equal to negative 1. And on that interval, you have one local minima, and you have one critical point on that interval. So you have an absolute minimum there. So you'll only have one absolute minimum all over, but it's going to be the same for both of these. So the minimum distance, will be the square root of 1 squared plus 1 over 1 squared, which is the square root of 1 plus 1 is the square root of 2. Now that's for x equals 1, but it's going to be the same for x equals minus 1 because you're squaring everything. So that tells us that we have 2 points that have minimal distance, and one of them is the point 1 comma 1, and the other one is the point minus 1 comma minus 1, and we can just say that this distance here so is the square root of 2, and same here. So there's only one minimum distance, which is the square root of 2. It's just that there are 2 different points that give us that minimum distance, and that's what it asked for. It said what points, and there we have it.